Now we reach random variables, which is perhaps, one can argue, the most important idea in probability theory. And we're going to define what a random variable is rigorously. In contrast to the way people might have used the language 200 years ago, where they had more of an intuitive feel for a random variable, we'll be able to define it using more rigorous language. A quick recap. Lecture 1 does not count because that was just an introduction. In Lecture 2, we talked about probability spaces. In a probability space, it consists of a sample space. It's just a set. And then you have a sigma algebra consisting of events. So those are the sets, the subsets of the sample space on which probability is defined. And then you have a function called the probability function that takes events and it assigns them to 0, 1, and it has to satisfy certain properties. In Lecture 2, we specialized to where instead of an arbitrary set, you had the real line, and instead of just an arbitrary sigma algebra, you had the sigma algebra that is generated when you consider intervals on the real line. We call that the Borel algebra. And then we talk about probability measures on such a space. So this is sort of, you restrict the previous lecture to R. This is sort of like the special case. And basically what Lecture 4 is, and this is what random variables really do, is you map. This is what a random variable is. It's a map from something that's abstract, which you want to think of as a sample space, into the real line, something that's very concrete. And the reason for doing this is because some random experiments are very difficult to work with directly when you work in the sample space itself. So for example, in probability theory, there's something called the branching process. I'm not sure if we're ever going to talk about this. It's not in the plan for the syllabus, but if we have time, which almost never happens in a math class, right? When did you ever have a math class where you actually had time to do anything beyond the syllabus? But if we have time, this is something we can talk about. A branching process is basically, without defining it in a rigorous way, but basically you start with one cell, you can call it the cell, and then that cell randomly produces children. So the number of children is random. It might produce 0 children, in which the process terminates, but maybe it produces 3 children. And then each of those children produce a random number of children. So this can be maybe 2 children, maybe this one produces 1, maybe this one produces 3. On the next level, maybe this one produces 1, this one produces none, this one produces none, and maybe the last one produces 2. And on the next level, they do not produce anything, and then this process becomes extinct, right? It just goes extinction. But then you can imagine that you can have a tree that sort of goes on forever, like this perhaps, and so on. So a branching process, I mean, this is basically what a branching process is. You start with a cell, and that cell randomly reproduces into new cells. It could be 0, it could be more than 1. And then each of those cells randomly reproduces to new cells, and the process can go extinct, it terminates, or it just goes on forever. And the sample space is actually quite complicated. The sample space, this would be the set of all such trees that you can get. This is a very complicated set. This is actually an uncountable set. We're not going to prove it because we do not need to, but I'm just giving you a fact that this is an uncountable set. It is an absolutely enormous set. And if you want to define, if you want to be able to represent such trees chosen at random, you will also need a sigma algebra. So you have to determine, you have to not just work with the trees, but you have to work with sets of trees. And those sets of trees, you have to determine which of those are going to be part of your sigma algebra, and then you have a follow-up confusion of how is the probability measure defined. You're not going to be defining it on the tree. You're actually going to be defining it on an event. So then you have to figure out how the probability measure has to be defined so you can capture the intuitive idea of something like this. And that's very difficult to work with directly. So that would be one such example where the sample space is very difficult, right? This is very difficult to work with directly. Another example is this comes up in the mathematical models of finance. They also call this Brownian motion. We do hope to talk about this at some point, but when one talks about the motion of a stock price, it sort of randomly fluctuates over time. So in a way, what this is this is a random path. And then the sample space would just be the set, right? This will be the set of all such paths. That's, of course, an uncountable set for one simple reason, because they're indexed by the real numbers. So for every real number, you have a value. And it would be a little bit hard to work with something like this directly. So rather what we do is we define a function. We define a function from the sample space into the real line. And this is what a random variable basically is. For notation, we're going to use capital letters like X, Y, Z to denote a random variable, even though you could argue maybe we should call it F. That's the notation that people use in probability theory. So it's a function, and what it's doing is it is assigning to each possibility in your sample space a observable real outcome, something which it is easier to work with. So for example, if you talk about these random paths and you think of this as representing the stock prices, and you go up to some future time, let's call it capital T, maybe you're interested in the maximum that you get, the maximum price or something. So let's say that's $20 or something. $20 beyond its initial value. So what you're then doing is you're taking every element of the sample space, you're observing a quantity associated with it that you might care about, and so you're mapping each sample point into the real line. When you go back to the example with a branching process, what you might be interested in, so let's draw a picture of a tree. Maybe what you're interested in is X will represent how many generations you have before it goes extinct. So here you have 1, 2, 3 generations. Now, if the process goes on forever, then the value of X would be infinite. So you could also define a random variable to go into the extended real line. As we said last time, we did talk about probability measures on the real line, but you can very easily extend that definition and talk about probability measures on the extended real line that includes plus and minus infinity. So X would therefore take such a tree and it would assign it to the number of generations that you have. And maybe if it goes on forever, then X could also take on an infinite value. And this is something that's like more manageable to work with because it's easier to understand. And that's what a random variable is. To give a definition, so we start with a random experiment, and a random experiment is denoted by a triple: sample space, sigma algebra, probability measure, be a probability space, and a random variable let's call it X on this sample space, on this probability space, is a function, is a map from the sample space to the real line. Now, recall that we equip the real line with the Borel algebra. And we want the following property to be satisfied. So that if we pick a subset of the real line, let's call it E. This is in the Borel algebra. So this is going to be a Borel set. So E is a subset of R, and it is a Borel set. So if you pick something that's a Borel set over here, then if you pull it back, you're going to get a subset of the sample space, and you want it to be something that lands in the sigma algebra. So to put it very simply, the pullback of an event. So an event is quite simply a subset that belongs to your sigma algebra. So we have two different sigma algebras. We have a sigma algebra on omega, which is our abstract space, and we have a sigma algebra on the real line, and specifically the Borel algebra. And an element of that sigma algebra is called an event. So we're saying the pullback of an event is another event. Now, if in case you're not familiar with what this notation means, I'm sure you know what that means. So where X inverse E, this is by definition, this is the way you define it, these would be points in the sample space with the property that the function at P will end up in E. So you call that the pullback. Some people call it the inverse image. Some people call that the pre-image, whatever language you want to use for that. For those of you who might have seen something like this before, this is very similar. So if you are familiar with point set topology, this definition is similar to continuity. So the pullback of an open set is open. Except here we're not talking about open sets, we're talking about events. Events are those things that belong to your sigma algebra. But it's very similar to that. So it plays the role of continuity as one does in topology. If you do not know what I'm talking about, that's not a big deal. You can just ignore that. So this is the definition of a random variable. Now, why does it have the name that it has? Well, to give you a very easy example, here's an easy example. So let omega be the sample space of tossing two, instead of cubical, so let's use something smaller so we have fewer numbers to deal with, two tetrahedral dice. So if you write this out, you're tossing two of them, so you're going to have pairs, 1, 1, 1, 2, 4, 4. So you have two dice, and this just represents, you can distinguish between them. So maybe one of them is red colored, and the other one is blue colored. So you're just introducing colors so you can distinguish between them. And this one over here is the red one, and the second coordinate represents the blue one. So whenever you toss these two dice and you have numbers from 1 to 4, instead of looking at the number that faces face up, there is no up here, but you can always look at the side that points down, right? The side that's lying flat on the table. So there's 4 numbers, so there's 4 outcomes. And because of symmetry, these are all equally likely. So the probability measure that you would put on the sample space would be a uniform measure where the probability of an event only depends on how many elements are in the event. It's pretty clear what the sigma algebra is. I'm not even going to write this out. The sigma algebra here will actually consist of every conceivable subset because this is a very simple sample space. It's a finite sample space. And the probability measure here is just a uniform measure where you just count. It's just simple counting. So this would be the way you describe this random experiment. And now you can define a map from this sample space to the real line, where x of an outcome, which can be denoted as a comma b, these are the two numbers that you get, is then the sum of the two numbers. Okay, so you can just say in words that x, this is the sum of tossing two tetrahedral dice. Okay, so in the old days, this is the way people thought of a random variable. Before you had mathematical rigor, so this is like the intuitive definition. You would say a random variable is something that keeps producing random numbers each time you do it. So it keeps on producing numbers. Like if you're tossing coins, or even to go back to our example over here, when you toss a pair of dice, these are not numbers. These are pairs of numbers, but they're not real numbers. But when you add them together, let's say, now you have a number. Okay, now you have a number. So in some way, it's you can call it a random, I mean, if you want, you might even call it like a random number generator. That's what a random variable is. It's a way of generating random numbers. It's called a random variable because you can see that each time you do this random experiment, the value of x is going to be something different. So let's say you do this random experiment and you get 1, 2. Then x would be equal to 3. If you do the random experiment again, maybe you'll get 4, 4, in which case the value of x is going to be 16, so on and so forth. So if you only observe the numbers that x produces, you really, in effect, have a random number generator. And that's what we call a random variable. Now, it's a little bit funny because usually the input that goes into a function is called a variable, and then you call this a function. So the terminology is a bit funny. So you can say technically x is a random function, but for historical reasons, we call it a variable, a random variable. When you have a function, and you have, so you would typically call this the variable, right? The points in the sample space are the variable because x is being evaluated at the sample points. But this is the way people thought of random variables in the old days. It's just a methodology for generating random numbers. And that's the way the definition has stuck. But when you make it rigorous, and in the modern language of probability theory, you say that a random variable is a function on the sample space, then it is a little bit strange to call it a variable, but that's the way we use the language. Okay, so that's what that is. And here's a very simple observation. Here's a simple observation. Oh, I did forget to say, why is it that the random variable that we just described is indeed a random variable? So we had this map from the sample space of all dice throws into the real numbers. So why is it that x inverse of an event belongs to the sigma algebra? This is actually quite simple because in this case, the sigma algebra for this event is the power set. It consists of every subset. So no matter what the event is, no matter what Borel set you pick, if you pull it back, it's a subset. And because it's a subset, it's automatically in the sigma algebra. So there's not much more to be said about that. But in general, you do have to verify that the pullback of an event is an event. So this is the simple observation. So to show that you have a random variable, i.e., that the pullback of an event belongs to the sigma algebra for every event, so for every Borel set. Okay, so this is a Borel set. This is a subset of the real line. And when you pull it back, this is a subset of the sample space. And this is the sigma algebra on the sample space. So for every event. So in order to verify this, it is sufficient to verify this condition, this property, when E is an interval. So you can just assume that it's an interval. You do not have to assume that it's just an arbitrary Borel set. You can make it easier for yourself and just assume it's an interval. And the reason is actually very simple, because it has to do with the fact that if you take a pullback, if you take the pullback of a union, it's the union of the pullbacks. If you take the pullback of an intersection, it's the intersection of the pullbacks. And since a Borel set is made out of countable intersections and unions involving intervals, you can just assume that you're having an interval. Because if you can prove it for intervals, then it will mean it's true for unions of intervals, and then for intersections of intervals, and then all of that. So that's why you can just assume that E is an interval, and you make it easier upon yourself. And this is going to be a homework problem. I'm going to write this as a proposition. I'll put it on the homework, and you can prove it. It's not difficult. In fact, it is sufficient to assume that E, it's a very special interval. It's the interval from negative infinity up to some number x, for some x. In other words, if the inverse image of this is in the sigma algebra for every x, so no matter what x you pick, then the conclusion is x is a random variable. So what we're basically saying is, if you want to show that something is a random variable, first you can reduce it to the case where E, where the event is an interval, and furthermore, you can assume it's an interval of this form. And then you have even fewer things to check. And this is just another way of saying, you can rewrite this. This is just the event that x is less than or equal to little x. It's the set of points that satisfies this. So you would just say that this is, right? I mean, this is the set of points in the sample space where x at the point is less than or equal to x. Right? You're saying x, right? X applied to a point is in this interval. But if it's in that interval, it at the very most it's x, and there is no lower bound. So it's just this. So you have to verify that sets of this form are in your sigma algebra, and you can verify, and if you can verify that, then it will mean that it's true for every interval. So it's not difficult to show. You can try doing that yourself. The next topic that we're going to discuss is we're going to discuss what is known as the distribution. The distribution of a random variable. If you've taken an undergraduate course in probability theory, you've definitely seen this before. Maybe if you've never even taken a course in probability theory, I'm sure you've heard of that word before, and you probably have some intuitive sense of what that is supposed to represent. So we're going to give the most sophisticated definition. This will include what you do in an undergraduate class and far beyond that. So this is going to be our definition. Maybe I should begin with a proposition first. Proposition: let omega script A and P be a probability space, and X from the sample space into the real line. And as we remarked, it is possible to replace this by the extended real line as well if you need to, is a random variable. So the idea is we're taking this abstract space, which can consist of anything. It's a set of really of anything. And you're assigning to those sample points a real number. So you're assigning real quantities to all of the sample points. And so you're mapping your sample space to the real line, and then you're observing the random experiment being done on the real line. Okay, so we have a random variable. Then X induces, maybe I'll write this a little bit better, a probability measure on the Borel algebra. Let's call it P subscript X, as follows. So the word induces in mathematics is used a lot if you've never seen this word before. It basically means you're using one type of structure to create a new kind of structure. So here's what's going on. At the moment, we have a probability measure on this abstract space. We have the real line with the Borel algebra, but there is no probability measure on this. This is actually what we talked about in the previous lecture. So in our first lecture, in our first real lecture, I mean, the first lecture was technically an introduction, but our first real lecture, we talked about what it means to be a probability measure on this. And then in our follow-up lecture, we talked about probability measures on the Borel algebra. And at the moment, we have a probability measure on this abstract space, on this abstract sample space. And we're going to use it. This is what we mean by induce. We're going to use an old type of structure to create a new type of structure on the Borel algebra. And we're going to call it P subscript X because this probability measure that we're about to construct, it is coming from this random variable. So we're using the random variable to construct for us a probability measure on the Borel algebra. And this is the way we do it. So this as follows. So we're going to say that if E is an event in the Borel algebra, because to be a probability measure on the Borel algebra, I have to tell you what Px does to an element in this sigma algebra, right? You pick something in the sigma algebra, and I have to tell you what Px does to that event. So if I'm going to pick something in here, and now I have to tell you what this does to that. So then Px of E is equal to, and this is by definition, this is the way we construct it, you're going to take the event and you're going to pull it back using the random variable. Okay, so we need to understand that this event, it's in the Borel algebra, so that means the event is a subset of R. So it's a subset of R, and we have a mapping from the sample space into the real line. So this event is living on the real line, and you're pulling it back using the random variable. And now this is a subset of the sample space. Now, because we have a random variable, by definition, it means that it pulls back sets in the Borel algebra to sets in the sigma algebra. So whatever this set is, it is by definition of what it means to be a random variable. It is contained in the sigma algebra. So that means we're able to apply the probability measure to that. So then we go ahead and we just apply the probability measure, the old measure, to that. Okay, so that's the idea. And the proof of this is actually very simple. So what do we have to prove? We have to prove that Px, we need to show that Px, and this is the new probability measure, is indeed a probability measure on the Borel algebra. Because if we're going to call it a probability measure, then it has to satisfy all of the properties that we've talked about. And I'm going to leave this up for homework because this is very, very easy to show. You can show this yourself. This is just a matter of verifying the definitions. Sometimes we call this, let's make a definition here. So we call Px the push forward of x. Maybe that's not the best way to put it, because it really is coming from, it's really coming from both of these. So maybe what we can say is so let's do it like this. So under the assumptions that we have a random variable on this sample space. So here I'm abusing notation. What I mean is that x, technically x, is mapping the sample space to the real line. But the reason why I'm putting this in here is I'm just saying that this is the additional assumptions that we're making. So we're making the assumption that this is not just a mapping from a sample space to the real line, but that it also respects the sigma algebras. In other words, if you pick something in here, it gets pulled back to something here. And then you're also further assuming that you currently have a probability measure on this. I just do not want to write all of that out. So we just use abusive notation to denote that. And we understand from context what we mean. So this is just like, you can say, a very shorthand notation for just saying you have a mapping from here to here that respects the sigma algebras and all that. So under the assumption that we have this random variable, we call P subscript x the push forward maybe instead of the push forward or something, I'll just call it the push forward. The push forward of all of this data. It's not one thing. You need like a whole list of things. You need a sample space, a sigma algebra, a probability measure, a random variable. You need all of that. So under all of those assumptions, you can talk about the push forward of this mapping. And so you end up creating a probability measure over here. So this new probability measure, Px, is a probability measure on the Borel algebra. And it is commonly called the distribution of x. So this is perhaps the most sophisticated definition of a distribution, that a random variable, it induces a new measure, and this new measure is now a measure on the Borel algebra. And the measure that you get on the Borel algebra is what you call the distribution of your random variable. And if you are familiar with like the undergraduate definition of distribution, you should convince yourself that this really does include the definition you might have seen before in the past. This is just a more sophisticated way of defining it. The idea here is, of course, the random variable is mapping your abstract experiment onto the real line, and then you're just investigating what happens on the real line. So the point of the distribution is to map everything back to the real line, investigate what happens on the real line, and the random experiment that describes it will be described by an appropriate probability measure. And the name of that measure is what you call the push forward. Now, maybe what would be helpful is to give you some examples of what we're doing. So let's give a very simple example of this. So consider the random experiment of tossing a pair of two tetrahedral dice, and let x be the sum of their values. So this would be an example of a random variable. So to describe the random experiment, we first need a sample space. So the sample space can be described as a pair, right? You're tossing a pair. So you can represent that every tetrahedral die has a number from 1 to 4 on it. So you can represent it. So this, you can distinguish between them. You can say that one of them is, let's say, red. It's a red die. And the other one is a blue die. So you can tell them apart. And then maybe the first coordinate is referring to the red one, and the second coordinate is referring to the blue one. And then your random experiment will just consist of all of these possibilities. And there's going to be a total of 16 of them. And all of these are equally likely because of symmetry, right? Getting any one of these single outcomes is going to be exactly the same. This is a symmetrical tetrahedral die. So that's going to be the sample space. The sigma algebra here would actually just be the power set of the sample space, because in this case, when it's a sample space with finitely many outcomes, you usually take the sigma algebra to just be the power set. Nothing funny really happens because everything's finite. And the probability measure, and P, the probability measure is defined by, in the reasonable way, that the probability of an event is then calculated by, you count the event and then you divide by the size of the sample space. So you would count the event, you would count how many sample points are in the event, and you divide it out by 16. Because all of these are equally likely, and so the probability of an event taking place is only determined by how many things are in the event, how many sample points are in the event. So hence this triple sigma, script A, and P describe formally, right? That this is the formal description of this random experiment. Often, this is the way we, like this right over here, this is like the intuitive problem. This is the way we think about it. And this over here is this is, you can say, the formal statement of this problem when you describe it more formally in the language, in the rigorous language of probability theory. So of course, in an undergraduate class, you always do it like this. But in a graduate probability class, you rewrite it in this language. So hence we have this triple, and this triple, this data, it formally describes this random experiment. Now, what is the random variable? So the idea here is that every single time this random experiment is done, you get a pair of numbers from the two dice. And if you add the two numbers together, you get an integer. You get a randomly generated integer, and this randomly generated integer is the value of x. So this would be a random variable. So, and x is the random variable that maps everything to the real line as follows. It takes a sample point, which is described by two integers, a and b, because everything in the sample space is a pair of two integers between 1 and 4. If you want to maybe be a little bit more rigorous, you should say x gets evaluated at this, which is a sample point. Sometimes we get sloppy and we use one set of brackets, but more carefully, this is what it is. X is evaluated at this pair, coming from the sample space, and it's equal to their sum. So as you can see, X is generating for you random real numbers. Every time you toss a pair of dice, you recalculate the value of X, and each time you get something different. Okay, so this is what we have. And clearly, X is a random variable. The reason for this is because to be a random variable, you need to check if you pick a Borel set on the real line and you pull it back, does it end up in the sigma algebra for the sample space? Well, the sigma algebra for the sample space here is the power set. It contains every subset. And so because of that, it will automatically be a random variable. There's nothing really to check. Let us find the distribution of X. So what do we mean by the distribution? We need to compute. So we need to find the push forward on the Borel algebra. Right? That's the definition of a distribution. You use the random variable to map the random experiment over onto the real line, and you use the original probability measure to calculate for you the measure of Borel sets. Okay, so how do we do that? Well, here's what we can observe. So if E is a Borel set, then Px applied to E is equal to, and this is by definition, this is how the push forward measure is defined. It's the original probability measure applied to its inverse. Okay, that's what you do. You have to pull it back. And now we're going to make an observation that I think maybe it would be good to consider the following example. So for instance, suppose that E is the following interval. Okay, this is an interval. It's not a pair. It's a little bit confusing because this notation means two different things. You can interpret this as a real interval, or you can interpret it as a pair of real numbers. So here it means it's the open interval. Is an open interval in the real line. Then the probability, this induced probability measure on E, that would be the probability of the inverse of E. But if you think about it, think about what you're asking, what is this supposed to represent? But X inverse of E is going to be empty. It's going to be empty because what's the definition of X? Well, let's just think about how this is defined. This is by definition, this is going to be the set of points in the sample space. Okay, so this pair means different from that pair. Okay, so this is the set of points in the sample space, so that when X is applied to that, it ends up in E. But to end up in E means it's between 1 and 2. So that would mean that X is between 1 and 2. But how is the random variable defined? The random variable is defined to be the sum of those two integers. And you get to see what the problem is. When you sum two integers, it's an integer. It cannot be between 1 and 2. There is no such pair. So it ends up being empty. So you can see that the probability of this entire event ends up being 0, right, under this induced measure. So thus, the probability of this entire event, E, will end up being 0, because we have an empty, when you pull it back, you get the empty set. Now, to use a different example, let's say instead of going from 1 to 2, we were to make this be the interval from 1 to 3, the open interval from 1 to 3. Then how would the calculation change? Then the pullback would be the set of points that are between 1 and 3. Right? It will be all of the points between 1 and... So the only numbers that satisfy this are 1, 1. 1, 2 is already too big. So this would just consist of the set only consisting of a single outcome, 1, 1. And then the probability of the event under this push forward measure would be the probability of this event 1, 1 in the original sample space. But this one only consists of just one sample point divided by 16 possibilities. Okay, and if you are starting to understand how this works, what you realize is the only numbers that matter in the event are the integers between 1 and 16. So like, for example, if we were to replace this by something that's bigger than 16, let's say we were to do this from 20 to 25, that would again be empty, because the sum, you cannot find a pair of points in the sample space whose sum would be between 20 and 25. So if you think about it carefully, this is what you should arrive at. So it's not difficult to see that this induced measure is a discrete probability measure on the Borel algebra. And it is, so the definition of a discrete measure is it is a sum of Dirac deltas. It is a sum of point masses. So the distribution here is going to be discrete. It is a sum of point masses. So the point masses that matter are the different possible values that this random variable can give. So it can add up to 2, it can add up to 3, and the most it can add up to is 16. So you would have the Dirac delta of 2, and the correct weight you have to assign is 1 over 16. Okay, it adds up to 2, and this is with the probability that it occurs with. And then you would have the Dirac delta of 3, but this one is going to be 3 out of 16. I'm sorry, 2 out of 16. So let me explain that part, because like, consider this question: what is the induced probability measure applied to the singleton set 3? That would be equal to, by definition, the probability that the random variable is equal to exactly 3. I mean, you could say you would pull it back, so you would say it's the pullback of 3. But when you pull back a singleton point, that's the same thing as the probability that x is equal to exactly 3. If you still do not like that, you can write it out even more carefully. You can say this is the set of points in the sample space, so that x applied to that point is equal to exactly 3. And the set of such points would just be 1, 2 and 2, 1. And when you add that up, that would be 2 over 16. So that's the reason why there's mass at 3, because you're calculating the probability. This induced measure has mass at 3. You can talk about the probability of 3, of a singleton point. That's why where the Dirac delta comes in, and this is the probability with which that happens. And then you'll have other ones. You can also have delta 4. This is the Dirac delta at the number 4, and this would be 3 over 16, because you can add up to 4 as 1, 3, 2, 2, 3, 1. And this will continue And the largest one you can have is delta 8, 4 plus 4, which would happen as 1 over 16. So if you actually write this out, so maybe I should write it out completely, the next one would be 4 out of 16. The next one would be 3 out of 6. It will go down, so you can check that. 2 out of 16. And the last one will be 1 out of 16. So this is a discrete, this is what we call a discrete measure, because it's a sum of Dirac deltas. You can check that these add up to 1. 1, 2, 3, 4, that's 10, and 3 to 1 is 6, so 16 out of 16. So it's a sum of Dirac deltas. So this is an example of a random variable. Okay, so let's go back to this example again. So this example is an example of a random variable, and in this example we calculated its distribution. Its distribution was discrete because it was a discrete probability measure that you got in the Borel algebra. So this is the distribution. Okay, so this thing over here is what we call the distribution of x. I know this is a lot more sophisticated because this is not normally the way you learn about distributions in an undergraduate class. If you've ever seen them before, you probably define them a bit differently, but this is the most sophisticated version. I think this is the best way of doing it, most general way of doing it, that the distribution, it's just the induced measure, the induced probability measure on the real line. And it's discrete because it's a discrete probability measure. It's a sum of Dirac deltas, and that is what it is. Okay, this is our example of a discrete distribution. Now let's do an example of a continuous distribution. Something that normally in like probability classes they call continuous random variables, but technically they should be called absolutely continuous random variables. And I'll explain that part again. We did talk about it, but I'll explain it again. But let me show you an example. So in this example, we're going to do this. We're going to throw. So suppose a blindfolded person throws darts at a disc-shaped board of radius 1 unit, and let x be the distance of the dart from the center. So find the distribution. So let's find the distribution of x. So this is an interesting example. So the idea here is we actually saw something similar, but previously we had a unit circle, but this time we actually have a dartboard. So it's a disk, it's filled in. And the fact that the person is blindfolded is going to be important here because it means that the individual cannot consciously aim at any part of the board. So if you have a blindfold off, you might be trying to consciously aim at the center of the board. You're trying with all your effort to hit the center. Now you might not always hit it, but that's what you're trying to do. If a person has a lot of skill in the game, if you're a very skilled dart thrower, then most of your shots would land in the middle, right? Most of your shots will be somewhere in the middle, and maybe you have a few outliers where you got very unlucky, but most of your shots will be in the middle. That's how the random experiment is going to look like. There's a much higher concentration of those shots in the middle than off the middle. Now, if you're blindfolded, then you have no idea where the dart is going. And so if you were to look at this random experiment, it will be a uniform scatter of points everywhere. Okay, that's the idea. It'll be like a uniformly scattered points without any tendency of going anywhere in the disk. So this is sort of like the significance of the fact that it's a blindfolded person as opposed to a skilled dart thrower. Remember, a random experiment is anything that is unpredictable. It's something that you cannot predict. Even if a person has a lot of skill, you cannot predict where the dart is going to end up. There's going to be a greater chance that the dart will be closer to the middle than someone who is less skilled, but you cannot really predict where that's going to go. And the fact that you cannot predict it, that is what makes it a random experiment. It's something that cannot be predicted unless it happens. And whenever you have a random experiment, you have to quantify what you mean by random. And the way you do that is with a probability measure. We have to put the correct probability measure that captures what we mean by that. So we have to do this first. So this is the intuitive or the undergraduate way the problem will be formulated. But now let's reformulate this problem in the more rigorous language of probability theory. So first we need a sample space. So we're going to let the sample space, this will consist of complex numbers. I'm going to use complex notation. They will consist of complex numbers with the property that the norm of the complex number, the absolute value of the complex number, is bounded by 1. This is how you get the unit disk. That would be our sample space. Okay, so we have captured the set of possible outcomes. Now, you might say, if a person is throwing darts at this board, there's a very high chance that he will miss the board completely. And you're correct, but we're going to disregard that. We will only consider those shots that actually hit something. So we're always in a case where something is being hit. So the board has been hit every time it's thrown, and this is what we have. So this is going to be our sample space. And now we need a sigma algebra. So when you try to come up with the sigma algebra, you want to try to think of events that are very easy to compute the probability of. So here's how I'm going to do this. So let R1 be less than or equal to R2 be between 0 and 1, and theta 1 be less than or equal to theta 2 less than or equal to 2 pi less than or equal to 0. So we're going to use polar coordinates over here. So a polar rectangle, and I'm going to use the notation R1, R2 cross theta 1, theta 2. I am slightly abusing notation because usually an interval cross another interval is supposed to be a rectangle. It's supposed to be like a Cartesian rectangle. The problem is that it could happen that you start at a point that is inside the disk, but when you form the Cartesian rectangle, it spills out outside the disk. So it's not convenient to use Cartesian rectangles. So rather, I'm going to denote this cross notation for a polar rectangle. So this is just going to be defined as the set of points of the form re to the I theta, where r is between r1 and r2, and theta is between theta 1 and theta 2. So if you want to see this in the picture, so this is the center, you have one type of radius, you have another type of radius, like this, and then you have one type of angle, and you have another type of angle, and you can see they give you a polar rectangle. So that's your polar rectangle. Okay, that's what it is. We can always assume the radius is between 0 and 1, and the angle is between 0 and 2 pi. So this is what we have. And that's what we call a polar rectangle. And we're going to let A subscript 0 be the algebra. So this is not the sigma algebra. This is just the algebra generated by all polar rectangles. Okay, so we have our polar rectangles. So that would mean that the intersection of two polar rectangles is another polar rectangle. So if, let's say, you have a rectangle like this, and then you have a rectangle like that, as you can see, the intersection of two polar rectangles is another polar rectangle. It could happen that the intersection is empty. And if you take two polar rectangles and you take their union, you can get something that's more complicated. So you can take the union of those two. You can get something that's a lot more complicated. But actually, I do not want to spend too much time on this. So let me just say this is the sigma algebra generated by all polar rectangles. So basically, this is going to be your sample space. Then you want events that are easy to compute the probability of. So those are going to be polar rectangles. And then the sigma algebra is just the sigma algebra generated by all of those polar rectangles. And if you can use countably many of them, then you can form regular Cartesian rectangle. So if you have like a regular Cartesian rectangle, like this, let's say, then you can approximate it by polar rectangles, right? You can kind of imagine that you have one polar rectangle, you have another polar rectangle, and if you use like a countable number of these, and you can exhaust and you can fill it up. So by using a countable number of these, you can generate some fairly complicated subsets of that disk, okay? And it can be shown. So details omitted. I do not want to go through the details here because we've done this before. This is basically the Carey-Theodori extension theorem again. So it can be shown that there is a probability measure P on this sigma algebra, so that the probability of a polar rectangle is equal to. So basically, the idea here is we want to use these polar rectangles as a way to tell us what the probability should be. Like, what should it be if this is truly a random experiment being done by someone who's blindfolded? Well, if this random experiment is done by someone who's blindfolded, then the only thing that matters is how much area this polar rectangle takes up. It does not matter where exactly it is positioned in the disk, because a blindfolded person has no bias of where the dart goes. So the only thing that will matter is the area of the rectangle. And how would you calculate the area of the rectangle? Well, so how do you do it? It's the difference in the angles. So it's like a half. So it's like a half the difference in the radii squared multiplied by the difference in the angles. Right? I mean, I leave that up to you to see that this is the correct way to do it. This is just some basic geometry of how you will calculate the area of that polar rectangle. Of course, I'm assuming that these are closed intervals, but these can be open intervals, or you can make them be like half open. It does not matter. I just do not want to write out all of those cases. And this is what it should be equal to. So you have to actually go through the details if you want to be very careful about this, to show that it is possible to come up with a probability measure which is calculated by this rule on the polar rectangles, and it extends to a probability measure on the sigma algebra that's generated by all of these special type of events. So this is the description of the random experiment. But now we need a random variable. Okay? So now we need a random variable. So we have constructed a probability space, a sample space, a sigma algebra, and a probability measure, which captures this intuitive experiment. Of course, I should make the obvious remark is that in real life, it's not possible to hit a single point. A dart in real life does not have infinitely small size. It has some kind of thickness. So no matter how small you make the dart, no matter how sharp you make the dart, when you hit a point in the disk, and if I ask you what are the coordinates, you cannot really say what they are with absolute precision. So this description of the random experiment is more like a mathematical idealization of a perfect experiment with an infinitely thin dart. But it's an approximation to reality, of course. That's often what we do. We come up with these ideal scenarios where the math works out nicer. Okay, so this is going to be our probability space. And next, what we need is we need the random variable. The random variable x from the unit disk to the real line is defined as follows. So we have to say what it does to a point in the sample space. And a point in the sample space is given by a complex number of norm 1. So what does it do with that complex number? Well, what it does with that complex number is that it assigns it to its distance from the center. So it just calculates for you the norm, the absolute value of that complex number, and that gives you a real number. So this is what you end up with, okay? So the question then comes up is, so this is the question. So why is x a random variable? Now, what do we mean by a random variable? What we mean is, by definition, that if you give me a Borel set and you pull it back, you get a Borel set. I'm sorry, you get a set in the sigma algebra. So we pick, so without loss of generality, we pick an event in the Borel algebra to be an interval. So say E is an interval. It does not really matter if it's open or closed. The argument will be the same. Let's say it's closed. It's the closed interval from two numbers, A and B. Okay, with A less than or equal to B, B less than or equal to 1, and A bigger than or equal to 0. I'm going to explain what happens to you if these numbers are bigger than 0 and 1. But the reason why I'm focusing on this special case is because the norm of a complex number will be between 0 and 1, because this is a point inside the unit disk, so its norm is between 0 and 1. Then we'll investigate afterwards what happens if this interval exceeds those bounds. So then x inverse of E will be equal to the set of points in the unit disk with the property that x applied to that complex number z, which is the absolute value of z, is inside AB, is inside the event, which is just another way of saying you want points in the unit disk so that their absolute value is between A and B. So we're assuming for now, for simplicity, that A and B are numbers between, so this is 0, this is the center, so this is like, you're interested in that the complex number is between A and B, so it's somewhere, so that would be the pullback. This is basically the picture. The inner circle has radius A, the outer circle has radius B. But what is this? This is, of course, a polar rectangle. The radius goes from A to B, and the angle goes from 0 to 2 pi. And this is clearly in the sigma algebra, because the sigma algebra contains the polar rectangles and all sets that can be formed using countable unions and countable intersections of those types of sets. Okay, so that means that this is a random variable. We can always assume that the Borel set happens to be an interval, because a Borel set in general is generated by these intervals, so it's enough to just focus on the intervals. And what if these numbers exceed? So let's say we went from, let's say this went from a half to 2. Well, then we would have that we want to find complex numbers that are between 1/2 and 2. But then you have to realize that because z is a complex point in the unit disk, its absolute value never exceeds 1. So this inequality is automatically satisfied, so you only have to satisfy this one. So then you would just write that this just goes back to 1/2, 1. So if you go above the number, you just replace it by 1. You just bring it back down to 1. And in the exact same way, if this was negative, you would just replace it back by 0. So this is the reason why we can assume that our interval that we were picking is between 0 and 1. And this shows that this x is indeed a random variable. And what we're going to do next is we're going to find, so I'm going to clear this entire board and we'll start again. So the next part of the problem, so next we will compute the distribution of x, i.e. we will find the push forward, Px. This is the probability measure induced by x on the Borel algebra. Okay? And it will turn out that this probability measure is what we call absolutely continuous. So if you forgot what that means, this is what we've talked about in the previous lecture. When we talk about probability measures on the real line, we can have the two common ones that come up a lot are discrete measures and absolutely continuous measures. Those are not the only ones, but those are the ones that come up a lot. So discrete measures are the ones that are sums of Dirac deltas, and the absolutely continuous measures are the ones that satisfy. So in other words, i.e., the Radon-Nikodym derivative with respect to the Lebesgue measure exists. So what does that mean? That means, i.e., there is a function, f, that's non-negative on the real line, such that, so this function is called the Radon-Nikodym derivative of this measure with respect to the Lebesgue measure, such that the probability on any event, on any Borel set, can be calculated by integrating that Borel set of f with respect to the Lebesgue measure. So that's what we're claiming. We can find such a function that will do that for you. That's what it means to be absolutely continuous. Now, so here's like some advice, some helpful advice. So when it comes to doing computations, you're going to assume what you need, get the answer, and then justify your answer afterwards. Okay, so like, because you can argue, you can ask, how do you know that this induced measure is indeed absolutely continuous? Do you not have to prove it? And you're right, you do have to prove it. But here's what we're going to do. We're going to assume that this is true. We're going to assume that it's possible to determine this measure by integration in the Lebesgue sense, by integration of some function. Then we're going to find what that function is. And after we get the function, then you can go backwards and justify that the measure actually it behaves according to that rule. So here's how we do it. So we're just going to assume this for now, and after you get the answer, then you'll be able to justify it. This is often the way mathematics works, that you might not be sure if you're allowed to do something. So you just say, well, let me just assume that I could do it, see what I get. After I get my answer, then you can just verify that it actually works. So here's how this is going to go. So we are trying to find a function. Well, let me make this observation. So observe that that x maps the random variable. It maps your sample space, the unit disk, to a number between 0 and 1, right? Because the random variable calculates the norm of a complex number. That's a number between 0 and 1. So thus, it is reasonable to expect that this function f, this function is called the probability density function, the probability density function of the distribution, that this function f looks like, so this is the way it's going to look like. So it's a function on the real line, right? And as a function, we expect that it should be 0 here, this is 1, and it should be 0 over here. Because x, our random variable, it will produce for you a random number between 0 and 1. Right? It will produce for you some random number between 0 and 1, but it cannot produce anything for you beyond 1 or anything that's negative. So this PDF should be 0 here and should be 0 here. And furthermore, you should also realize that it's easier to get a bigger number than a smaller number. Because if you think about it, this is your disk. If you, in a blindfolded way, pick a point, you'll have more points on the outside than you have points on the inside, because points on the inside closer to the middle, they take up a smaller area than the points further on the outside. The points further on the outside, they take up more area. So more often than not, you're expected to be further away from one. You're expected to be further away from 0 than you're closer to 0. And so it means we should have an increasing function. So maybe our function goes like this, or maybe our function goes like this. It should be some kind of increasing function, or maybe it goes like a straight line, maybe it goes like this. It should be an increasing function. So that's what our intuition says before we even do the calculation. Now, how do we find this function? So here's what we're going to do. So recall, so let P be a point somewhere between 0 and 1. Okay, so let P be a point between 0 and 1. F of P, so what does F of P mean? Well, it would mean the probability density function evaluated at P, but what it means is that, so this is like the interpretation, the intuitive interpretation that we've used, that if you pick the point P, so again, we're doing intuitive arguments right now. We're going to get an answer, and then after we get the answer, we'll be able to backtrack and then justify it afterwards. Okay, so we're getting the point P over here. Now, it does not mean, I want to just remind you, it does not mean the probability. So it does not mean it's the probability measure evaluated at P. Right, we're trying to find the PDF function of this induced measure of the distribution. It does not mean the distribution evaluated at P. We talked about this before. This actually happens with probability 0. When you have a lot of random variables, they have no point masses whatsoever. And this is going to be one of those instances. We're sort of asking the question, what is the probability, like if you're on your dart, what is the probability that you hit a ring exactly P units away from the center, exactly P, not a little above, not a little below, but exactly P. And because it's infinitely thin, it's reasonable that the probability of it should be 0. Okay, so it does not mean the probability of that. Rather, it means something else. What it means is we're going to take this interval and we're going to thicken it up a little bit. So let's go to P plus epsilon and P minus epsilon. So we make our interval thick. This is an infinitesimally small interval. And then the probability, so you look at the distribution, you would say the probability of landing inside that interval between P minus epsilon to P plus epsilon. It does not matter whether you use an open interval or a closed interval here, because there's no mass at a single individual point. It's not going to change anything. So the probability of landing inside this infinitesimally small interval should be approximately equal to the thickness of the interval, which is 2 epsilon, right? That's how thick the interval is, epsilon, epsilon, 2 epsilon, multiplied by the probability density function, how high it is at that point. So multiplied by f of p, right? That's what f of p is supposed to mean. That's what that number is supposed to represent. And as you make epsilon smaller, this estimate becomes more accurate. And you sort of want to consider the limit as it goes down to 0. I mean, in a way, it feels like a derivative, right? It starts starting to feel like a derivative. And that's another one of the reasons why we call it the Radon-Nikodym derivative. But anyway, let's calculate this probability. So this is the probability. So this would be the probability that our random variable x is contained, that the value of the random variable x is between p plus epsilon and p minus epsilon, right? So I'm being sloppy over here, but I really mean to say this is, you're going to look at the events where all of the sample points, their value, the random variable, which is the norm of the complex number, falls between those two. So if you want to see it in the picture, this is how it's going to look like. So here you have p, you have your point p between 0 and 1, that gives you a ring, and you go a little bit further out by epsilon, and you go a little bit further in by epsilon, and you're kind of asking what's the probability you fall within this thickened, you thicken it up a little bit, the probability that you fall within that thickened ring. And this is a polar rectangle, so that would be equal to, well, it would be the outer radius, p plus epsilon squared, minus the inner radius, p minus epsilon squared. So it's the differences of the radius 1/2, and then multiplied by 2 pi. Right? It's basically like a half times 2, that goes away. So it's like pi r squared, but you're subtracting the 2 radius. So if you work this out, that would give us, oh, I forgot to do one more thing. I think I forgot to say this. So this is the area of the polar rectangle, but technically this is incorrect. It's the area of the polar rectangle in proportion to the area of the entire disk. And since that's a unit, that would just be pi. So I think I forgot to divide by pi when I was setting up the sigma algebra and what p is supposed to do on the sigma algebra. Of course, it has to be divided by pi so that it works out to be a probability measure. But if you work this out, the pi's cancel, the 2.5 cancel, and this would be the p squared will cancel, epsilon squared will cancel, and you're just left with, so you would be left with 2 epsilon p minus 2 epsilon p. So that would be 4 epsilon p, and that should be approximately equal to 2 epsilon f of p. And so, if you were to cancel away the epsilon and the 2, we get, so thus, it seems that f of p at a point should be equal to twice the point. Okay. And so the probability, so hence the probability density function for this distribution is given by, so this is the function, we said it's 0 over here, this is 1, it's 0 over here, and then between 0 and 1, it just goes up like this. We do not really care about what it does at the number 1 itself, because this is a random variable. I'm sorry, this is a probability measure that has no point mass, so do not really care what happens at a single point. But this is the way it goes. You can check that the area underneath this thing is exactly 1, because it's 1 across and 2 up. So the area of the triangle is exactly 1, which it is supposed to. Okay, so thus, okay, so we are claiming, so hence, we claim that if you have an event, that if E is a Borel set, then the probability, then the distribution, so the probability distribution that you get evaluated at that event, it can be calculated by integrating. So you want to make sure that this event falls between the interval 0 and 1. So the way you would just write it is you would just take the event and you intersect it with the interval from 0 to 1. It does not matter whether it's an open or a closed interval. It's not going to make a difference in the calculation. So you're just going to integrate over that intersection. Right, so basically I'm saying that if you have an event, so again, just pretend your event is an interval. You're just going to look at that part of the interval that falls between 0 and 1, and you're going to integrate. What are you going to integrate? You're going to integrate the function 2p, or if you prefer, in more classical notation, you would write 2x dx. This is the way you would write it. This is, of course, this is an uppercase x, this is a lowercase x. They have absolutely nothing to do with each other. If you do not like to use the letter x because it's confusing, use a different letter. So just write like 2t dt. This is like the more classical notation. So you're just integrating the function 2t over this event intersected with 0, 1. So that is what we're claiming. This is exactly what we mean by the distribution. You see, this is where the difference lies. In undergraduate probability theory, you would draw this picture and you would call this picture the distribution for x. We're being a little bit more sophisticated, and we are rather referring to this one as the distribution, and this is the probability density function for the distribution. Okay, so it's a slightly different choice of language. So we claim that, and then you just check it, right? And then you just have to check. You just have to check that the probability of every Borel set calculated based on the way the random experiment is being done will be equal to if you were to do that. And the way you check it is you can assume that E is an interval, right? You just assume that E is an interval. It's enough to just check it on intervals. And then if you calculate the probability of an interval, so when you calculate the probability of this, how do you do this? This would be by definition, this is the probability that X is in that, so that would be the pullback, right? That would be the pullback, that X inverse of E. And we talked about this already, the probability of the pullback. When you look at the picture of the pullback, it will just be an annulus. So you're calculating the probability of the annulus. And when you compute the probability of the annulus, that would be the exact same thing you would get if you were to integrate that function over that restricted interval. And then you see you get the same answer. So that's normally what you do. You kind of assume that the random variable is like absolutely continuous, so you have a probability density function, and then you reason out what it needs to be. And that's what happens. Now, if your assumption was wrong, if let's say it turns out that this random variable, well, this distribution is not absolutely continuous, so this does not exist, then if you were to make that assumption and you do your series of calculations, you will get an answer. But when you check that answer to see if it's consistent with what the measure is supposed to give you, you're going to get something that does not work out. And then that will mean that it's the random variable, the random variable does not induce an absolutely continuous distribution. That's what that would mean. But you always basically assume that the distribution that has the properties that you want it to have. You work it out. You use your intuition, right? You're using your intuition along the way about what you think needs to happen. You arrive at the calculation, and then you justify it afterwards after you get your answer. So that is what a random variable is and what a distribution of a random variable is. So the basic idea, so maybe to summarize, the basic idea is that we map the sample space onto the real line and then like reanalyze the random experiment on the real line. And that is what we call that. And the new probability measure we get on the real line is called the distribution. It's essentially, this is essentially the mapped version of the random experiment onto the real line. And when you're back, and when you return back to the real line, everything is easier to understand because you're back to working with the real numbers. The next topic we're going to talk about is called expectation. Expectation of random variables. And this is a very important number associated with a random variable. So the way this works is that x, this is a random variable. And as we said, intuitively, you want to think of a random variable as sort of like a random number generator, that it produces for you a real number every time a random experiment is being done. Whereas the expectation of x, this would be one way you write it. Some people might write it with square brackets. Does not really matter. The expectation of x, this is going to be a real number. So x is a random variable, and you can even intuitively maybe think of it as a random number, a random real number. Whereas the expectation of x, this is a real number. It's not random, it's just a real number. Okay? And this is what you call the expectation of a random variable. That's the way you say it. Now, before we define it, maybe I should give you an example. So in this example, we're going to toss two fair coins. And so you have two sides. One of them is heads, one of them is tails. But what you're going to do is, instead of calling them heads and tails, one of these sides, you're going to draw the number 1. And on the other side, you're going to draw the number 0. So instead of calling them heads and tails, you just call it 1 and 0. And you're going to let x, this is going to be the sum of the two numbers that you see on both of the coins. So to distinguish between the coins, it might make it easier to use, let's say, a dime, and then to use a quarter. So then when we write, let's say we write 0, 0, then the 0 represents the outcome on the dime, and this 0 represents the outcome on the quarter. So you have 4 possible outcomes here. And they all happen to be equally likely, by the way, because these are fair coins. And if you check what x is equal to, on this outcome, x is 0. On this outcome, x is 1. X is 1. And then this outcome, x is 2. So here's something you can ask. What do we expect? What do we expect x to be? I mean, we do not know what x is going to be. That's the whole point, because x is a random variable. It can take any number, 0, 1, or 2, and that happens randomly. But you can see that, well, what do we expect? Well, one thing we can see is that it's much more likely for it to be 1 than to be 0 or 2, because this one happens twice as often. But you can also ask this question from the point of averages. So on average, what happens? So if we think about it, if we were to do this experiment 1,000 times, what would happen if we do it 1,000 times? Well, roughly, a quarter of the time, so it'll be evenly divided, right? If you do it 1,000 times, then 250 would go into each one. Not exactly, but roughly, you'll have about 250 occurrences of every one of these 4 outcomes. So what would happen on average? Well, on average, we would see the number 0. So on average, what we would have is we would have 0 times 250, plus we would have 1 times 250, plus 1 times 250, plus 2 times 250. And then how many times did we do this random experiment? Well, we did it 1,000 times. So if you calculate what this is, 250, 250, 500, so that's 1,000 over 1,000. So on average, we would have 1. So we would expect that x should be equal to 1 on average. Okay, and you can kind of imagine why you would care about this in the real world. This is a silly example, but a more serious example is maybe x represents the price of a stock in the future. So the way you look at this is the world in which we live is just one out of many different worlds. Just like so in this experiment, there's 4 possible worlds in which you can occupy when the experiment is done. But the world in which we live is, in some sense, one of many different worlds that can happen, because the future stock price really could be anything. And then we're interested in, what do we expect the stock price to be? And if we can make a good estimate for that, we can make money on that if we think it's going to be on average above something, and then we're willing to buy it or sell it if we think on average it's going to be below something. So it's the same idea. So how do we define expectation in a rigorous way? Now, this is going to be done very differently from the way you've seen it done in an undergraduate class. This is, after all, a graduate class. We have more heavy mathematical machinery. So here's how we define expectation. So here's definition. Let omega script a comma p be a probability space. So I'm not going to remind you what that is. Again, we all know that. And x is a random variable. And since we're learning about random variables for our first time, to quickly recall what that means, it means x is a function that takes sample points and it assigns them to real numbers. That's basically what it means. There is another requirement, is that it has to respect the sigma algebra, which just basically means that if you pick a Borel set and you pull it back using this function, you end up with a subset of the sample space that then belongs to the sigma algebra. So there's that technical requirement to be a random variable. But basically what it means is that you have a function that assigns real quantities to sample points. And here's how you define it. So the expectation of x is equal to, by definition, it's equal to, and this is what you're going to do. So I'm going to write down the definition, and then I'll explain to you why this definition makes sense. So you're going to integrate the random variable over the sample space with respect to the probability measure. So first of all, what does this even mean? Now, previously, we talked about integrating functions on the real line with respect to a real measure. This means exactly the same thing. So what this means is, this is the idea behind it, is let's say this square represents your sample space. and then you cut up the sample space into pieces. We're going to call these events. I'm going to pick one of the events over here, EI. You cut it up into events that happen to sit inside the sigma algebra. And then for every event, you're going to pick a point inside the event. Let's call that point lowercase omega I. So capital omega is the sample space, lowercase omega is a point in the sample space, so it's a sample point. And then here's the way you can estimate the integral. You will form a Riemann sum. So you would take the random variable and you can evaluate it at that point, because this is a function on the sample space. So you can evaluate it at the point, at the sample point, and then you will multiply it by the probability measure of the event in which it is chosen from. And then you would sum over all of those. So you would cut it up into finitely many pieces. And then the idea is that this Riemann sum, it will approximate the value of the integral. Now, why is this the correct way to define expectation? Well, if you go back to the example that we just did with the two coins, the sample space was finite. It had a finite number of outcomes, 0, 0, 0, 1, 1, 0, 1, 1. So then you can break it into four, you can partition it into four events. So you would have one event that would just consist of the single point 0, 0. You will have another event that will consist of 1, 0, another event that will be a singleton set consisting of 0, 1, and then you have one more, which would be 1, 1. And then the way you would form the Riemann sum is, notice what would happen, the probability of each of these events, well, these are singletons, so you would just count how many, it's just a single point in the sample space of 4, so that would be 1/4. And then you will multiply it by x evaluated at a sample point. But because this is a singleton set, there's only one sample point you can pick. So when we run through the calculation, x on this sample point would be 0. On that sample point, the value of x, if x represents the sum, would be 1, 1, and 2. And then the calculation would lead to 0 out of 4 plus 1 out of 4 plus 1 out of 4 plus 2 out of 4. And that's how we end up getting the value of expectation. So this certainly makes a lot of sense. You can do this if it happens to be a finite sample space. Of course, in many random experiments, they're too complicated to be described by a finite number of outcomes. And that's why you use integration, because it's sort of the exact same idea. You're just using finite sums to approximate what's supposed to happen. This is supposed to be the limiting sum, so you break it up into pieces, into finitely many pieces, and by doing it, you are approximating the Riemann sum. And then there's theory that goes into how does one actually define integration rigorously, but that's what we mean. That's something that's more appropriate for a real analysis course, where you talk about measures in the abstract and integration of measures in the abstract. But this is basically the way you do it. And this is it makes sense. So this is the way you do it. Now, I do want to caution you, and I should say assuming this integral exists. The integral might not exist, in which case you would say the random variable has no expectation. That's what you would say. It has no expectation. That could happen. We'll probably see examples on the homework which will show you the expectation does not have to exist. Though the kind of examples one typically comes across in probability theory, the expectation does exist, so it's not something that's too serious, even though in theory it does not have to. In practice, the kind of random variables we deal with, they will have expectation. The integral might not exist because, of course, if this is an uncountable sample space and you try to partition it into pieces and take the Riemann sums, it is conceivable that maybe there's no limit as you do it. So let's show an example. I'm going to go back to this example that we did before. This was our example. We had blind folded dart throwing. Our sample space consisted of complex numbers with norm bounded by 1. We had a sigma algebra that I'm not going to write out. This was the sigma algebra that was generated by all of the polar rectangles. And then you had a probability measure that if you have a polar rectangle, which I'll just draw it like this. This is a polar rectangle. Then the probability measure of a polar rectangle is the area of the polar rectangle divided out by pi, which is the area of the dartboard. I think previously I forgot to write out divided by pi, but I'm sure you figured that out. So that's the way it is. So you define the probability measure on polar rectangles, and then you use the Carathéer-Doherty extension theorem to claim that you can extend the measure to the entire sigma algebra, and that's what it does on these special types of events. And we had a random variable, x, where if you have a point, let's call it z, if you have a point in the sample space, you calculate the distance to the center, so the absolute value of z. That was a random variable. And we can therefore ask, what is the expectation of x equal to? Let's try to understand what we're trying to ask. So here's what we're going to ask. We have a dartboard, and inside this dartboard, we're throwing random darts in a blindfolded way. So we have absolutely no preference where it ends up. It's just scattered all across the board. And one thing you should realize is that if you were to draw an inner circle, it takes up less area than the outer circle. And so it makes sense, it is intuitively clear, that the expectation, whatever it is, it has to be greater than 1/2. Because because x is measuring the distance to the center. Well, if you go halfway up, that takes up less area. So it therefore makes sense more of the shots should be outside that circle. So on average, it should be greater than 1/2. What is the actual number? So as we will show, the expectation is equal to 2/3. So we will see that the expectation turns out being equal to exactly 2/3. And then interestingly, you can do this random experiment on a computer, and I'll show you later how to do that. You can do this random experiment on a computer, and when you do it on the computer and you average out the numbers, you will see that it does indeed. It's never going to give you exactly 2/3, but when you do these simulations on the computer, you will see it's very close to 2/3, confirming what the math theory tells us. So the question here is, how do we justify this? So the way you justify this is you have to go back to the definition of expectation. You would have to integrate. So what you have to do here is you have to integrate x over the sample space using this measure. Question is, how does one do something like this? So this is what we're going to do, and this goes back to the theme that we were saying earlier. What we often bring the problem back to the real line. We bring everything back to the real line. And then we solve the problem on the real line. So I'm going to just say, I'm going to tell you what I'm going to kind of do it first, and then I'll justify it afterwards. So you would bring it back to the real line. And then you would look at the distribution. So the random variable gives you a distribution, which we call p subscript x. P subscript x. It will give you a distribution. And then what function do we integrate? Well, we integrate just the identity function. If that's not clear why it's the identity function, I will justify that afterwards. But essentially, maybe to explain to you what's happening, I'll give you like some intuition why we're integrating the identity function, because this square is your sample space, and this is the real line. And the random variable, it maps everything to the real line. So now, if you give me a point on the real line, like let's say lowercase x is one possible value. It's like a random value that can be produced using this random variable. And that random value came from a certain sample point. So you do x evaluated at that sample point, and then you multiply it by how likely, right? You kind of enclose it off in a small little event, and that puts it inside some interval here. but then you multiply it by how likely that number is to happen. But instead of being the length of the interval, it's more like the new measure associated with the interval. That's basically what you do. If you do not like that argument, I'll give you another argument afterwards that will be more satisfactory. But what do you do after this? Well, the way you carry on the calculation is previously we found that the Radon-Nikodym derivative of the distribution with respect to the Lebesgue measure was this function f, where f is the function that is defined as follows. It is equal to x if x is between, I'm sorry, it was 2x if x is between 0 and 1, and 0 if otherwise. So this was the function that goes like this. It's 0 over here, and it's 0 over here. We do not care about what it does at the endpoints, because when we integrate, it's not going to influence anything. So this is what we've shown previously in today's lecture, that the Radon-Nikodym derivative of this measure with respect to the Lebesgue measure is this function f. And then you basically do integration like the way you're used to, that you would say that this is the integral of the real, on the real line, of the identity function, and then you would replace dpx by f d lambda, by f d lambda. This is the way you would do it. Okay, so this is f d lambda, and then you can do the calculation. So the identity function, that's just x, right? So like, how would you write this? So normally you write this as the integral from negative infinity to infinity. The identity function, that's just x, right? That's just the function x. Then you have f of x and Lebesgue measure. So normally you write the integral like dx or something. And now when you do the integral, you notice that this function is 0 outside those bounds. And so you end up with integral from 0 to 1, x times 2x. And then you know how to do that integral. So that's 2x squared, so that would be 2/3. So that's how you end up getting 2/3. Okay, so there were a number of steps involved in these calculations. So the step going from here to here, this is the symbolic justification for that, that you replace dpx by the Radon-Nikodym derivative. So this, of course, has to be justified, but that's something that's done in a real analysis course. But there was another step here. How do you go from this one to this one? Like, how do you convert that one to the one that looks like this? So that's what I wanted to talk about here. So this is what we call change of variables. This is called change of variables in integration. It's very similar to change of variables that one does with ordinary calculus. So basically the question here is, how do you justify this step? So let's just go back to calculus 1. So in calculus, we often substitute in integration. And the way this works is, let's say you're integrating on an interval and you have a function, and when you take calculus, you always put that dx at the end. And the purpose of that dx is to serve as a symbolic to do substitution for you. So let's say you want to substitute, let's say you take x and you replace it by a new function, g of y, then you would write that this is f of g of y, but then you also have to change the dx. So then you would write this as g prime. So you differentiate the function and you write dy. And then the limits change. So the limits would be, let's say, a prime, b prime, where a prime and b prime, maybe I should not call them prime because that looks like a derivative, but maybe I'll call them a0, b0, where a0, b0 satisfy the following condition that you want. Well, basically, it just has to respect the substitution. So if x, so you see, if x is equal to a, then y should be equal to a0. So basically, that's what we're saying, that if you substitute a for x, that should give you the same thing if you were to substitute this lower limit in place of y, right? So that's how you get the new bounds. So this is what you call integration by substitution. And this is a special case of something that's really a lot more general, that you have the same situation that takes place with measures. So we can call this the change of variables for measure spaces. And this is the setup. So the setup is you have a measure space. So you have a sample space, you have a sigma algebra, and then you have a measure here, mu1. Now, in general, this could be a measure. It does not have to be a probability measure, but if you want, you can just pretend that mu1 is a probability measure. If you want, you can call it like p1 or something. Does not really matter. I'm just going to call it mu1. And then you have another measure, another probability space or a measure space, however you want to put it. And you have a transformation. I'm going to call it T for transformation. So what do we mean by this? So here's what we mean. T is a map from omega 1 to omega 2. That's the first thing that happens. The second thing that happens is T respects, so let's say this is 1. The second thing is if we pick an event in the second sigma algebra and we pull it back using T, then we get an event in the first sigma algebra. So it respects the sigma algebras. And the third one, you want to say that, so you want to be able to say that omega 2 is the push forward of omega 1. This is the push forward, I'm sorry, mu1. In other words, if you want to calculate the probability or the measure, depending how you want to think about it, of some event, that's the same thing as pulling the event back using this transformation, and then using the first measure to calculate the measure of that event. Okay, so this is why we have a transformation. Okay, so this is the setup. And what we have here is, let us say that f is a real valued function defined on omega 2. If you want to be a little bit more careful, I do not want to write down every single hypothesis, but this should be, of course, measurable. It should be a measurable real valued function. So what that would just mean is, you can probably guess what this means, is you have a function from omega 2 to the real line, and measurable will just mean that if you have a Borel set and you pull it back, then you get something in the event in this sigma algebra. Okay, so it's not just it's not just an arbitrary. I should be careful. I should not say random. It's not just like an arbitrary real valued function. It should be measurable in this sense. But basically, a real valued function. And this is what's going to happen. So then, if you wanted to integrate this real valued function over omega 2 with respect to this measure, and as before, what does this even mean? What this means is you partition omega 2 into a finite number of events. You pick points in every one of those events. You then evaluate them using the function that gives you a Riemann sum. And the limiting process as you do that, that's what you call the integral of that, assuming it exists, right? That's basically what you do. And what we're saying is that this is equal to the same thing as integrating over omega 1 using the first measure, but it's going to be f composed with this transformation. So you do the transformation first. You see this? The transformation takes you from omega, it goes from omega 1 to omega 2, and then the f takes you from omega 2 into the real line. So this composition is giving you a real valued function from omega 1 directly into the real line. And if you take that function and you integrate it using the first measure, that's the same thing as if you were just to integrate the function using the second measure. So this is what we have. And this is referred to as change of variables in integration. This is what we have. And it's not particularly difficult to prove. It's just that you have to develop a theory. You have to carefully develop a theory of integration. But what's interesting is maybe you can prove this yourself using a heuristic style argument. Maybe you can give like a plausible sounding argument that's not rigorous why you expect both of these to be correct. So that's very, very believable. And that should be a little bit reminiscent of integration in calculus the way you're used to. So why do I bring this up? So the reason why I'm bringing this up is because this is exactly what happens when you're integrating random variables. When you're integrating a random variable, this is the situation. You have a sample space, you have a sigma algebra, you have a probability measure, and then you have a random variable x. Now the random variable x, it's a transformation to the real line with the Borel algebra, and you get a new measure on the real line, which is what we call the distribution, right? That's what we call the distribution measure. So we're in this situation where you have a transformation from this measure space to that measure space. In this case, they happen to be probability spaces. So we have a transformation from this probability space to that probability space. And you're integrating a function. So what exactly are you integrating? Well, you're integrating the identity function. You just have the identity function to the real line, right? And now look what happens. If you integrate the identity function on the real line, right? So this is the function that you're integrating. So you're integrating the identity function on the real line using with respect to that measure, dpx. That's the same thing as integrating, doing this composition like this, going from the original sample space directly to the real line. So that would be identity composed x, like this, going directly like that, and then integrating with respect to the measure you had in the beginning, dp. So that's what you're doing. And, well, because you're composing with the identity function, that's really just the same thing as just integrating x with respect to the original measure. And this is what we did. So when we're integrating a random variable with respect to this measure, with respect to this probability space, that's the same thing as just integrating the identity function on the real line with respect to the distribution that you're getting that arises from that random variable. So this is what's happening here. In fact, you can be a little bit more general with everything that we're doing. More generally, this does not even have to be the identity function. This could be an arbitrary function. Let me call this function g. I do not want to call it f because sometimes we use f to denote the probability density function of this. But let's just call it g. So if you want to integrate g, like that would be the same thing as doing this composition, doing this followed by this, the composition, which we could just write maybe g of x like this, or if you prefer, you can write g composed x, but g of x. So that's the way you can write that. Yeah, so that's the change of variable theorem. Okay, so this is the way that this works. And maybe I can briefly summarize. So to briefly summarize, so assuming x is what we call an absolutely continuous random variable, what does that mean? It means, i.e., the distribution is, so the distribution has a redundant Kadim derivative. Maybe what I can just say is that the distribution function maybe I'll write it using this notation. In other words, if you look at the distribution function, it's differentiable with respect to the Lebesgue measure that this exists. And f is the probability density function of x. So in other words, what that means is that f represents this. It represents this. Then the way you can find the expectation of x, this is the way you do it, is you pretty much just integrate on the real line, and you do x, f of x, in the usual way. So why does this work? So the reason why this works is because the expectation of x is you integrate over the sample space with respect to the measure, and then you can convert it back to the real line. You integrate the identity function with respect to the distribution, the probability measure that arises from the random variable. And then because you have a Radon-Nikodym derivative, you can just write this as integrating over R. It's the identity function multiplied by f with respect to the Lebesgue measure. And then when you write it out in classical calculus notation, you would write this as an integral from -infinity to infinity. The identity function is given by the formula x, and this is the function f of x. And then you just write like dx just symbolically, but that's the way you would write it. And more generally, that if you want to find the expectation, if you wanted to apply, let's say, some function apply to your random variable, in other words, a composition, a real valued function composed with a random variable, then what would happen is you would just apply this function just to that x. So you would just write it as the integral of g of x, f of x, like this. So if that's not clear, what you're doing is this is basically g composed with x. G is a real valued function composed with x. And then based on the change of variable theorem, this would be integrating g composed x dp. And then the change of variable theorem would say is you keep the g, you just keep the real valued function, and you integrate it with respect to the measure that you're getting on the real line arising from the random variable. That's what you call the distribution. The distribution is the induced measure. And then assuming the Radon-Nikodym derivative exists, that's what we call an absolutely continuous random variable. This function, by the way, you call that the PDF, the probability density function of x. You would then replace it by that function. But instead of the identity function here, you just have g. And then in classical notation, this would be the integral from -infinity to infinity. This would be g of x multiplied against f of x. And then you just put the classical dx at the end, and that whatever you do that calculation, you would get this. Again, assuming that they exist, right? This might not exist, this one might not exist, but that's basically the way you would do it. So this is the situation which is very common in probability theory. If the random variable, by the way, was discrete, then you can probably guess what you do. I'm not even going to write it out. But if it was a discrete random variable, you would replace these by infinite sums, by infinite series, or by finite sums, and then you would have a very similar situation. So this is how you calculate expectation. Now, I also want to mention some properties of expectation. So the first property of expectation is if x is a constant. Now, you might find this a little bit confusing. What exactly do we mean by constant? Well, what we mean is that a random variable is, after all, a map from the sample space to the real line. It's just a function. And we're saying this is a constant function that always returns the same number no matter what you do. It's a little bit funny calling it a random variable because it always gives you the same number. One would typically not call that random, but it fits our definition. It is, after all, a function on the sample space. And if x is a constant, then the expectation of that random variable would just be equal to whatever constant value that is. That should not be surprising. That should make sense. If the random variable always produces for you the number 5, then the average out of all of the numbers you see would be the number 5. That just makes a lot of sense. The second property is that if you take the expectation of a sum of two random variables. Now, what do we mean by adding two random variables together? Well, this is a function and that is a function, right? These are functions. And this is just the sum of the two functions. You're just adding two functions together. So how do you then determine what this does to a sample point? Well, you evaluate it using x, you evaluate it using y, and then you have two numbers that you can add together. There is a little bit of a proof involved. You do have to show that the sum of two random variables is, again, a random variable. That does take a justification. That's not immediate, because it does have to satisfy the property that the pullback of a measurable set is a measurable set. But if you're willing to accept that, then that would mean that the expectation of the sum is the sum of the expectations. Why is this believable? Well, because that's exactly how integration works. What is this supposed to be? This is supposed to be the integral of their sum with respect to the probability measure. But the integration of a sum should be the sum of the integrals, right? This is just the usual properties of integration. And then the other one, which is similar, is that if you have an expectation of a random variable and you multiply it by a scalar, let's call that scalar c for constant, you multiply it, you rescale it, and you can probably guess what this means. And again, it requires a little bit of a justification to show that if this is a random variable, then rescaling a random variable is again a random variable. But if you're willing to accept that, then that's the same thing as factoring out the constant. That's fairly believable because that's exactly how integration works. You can factor out constants out of integration. And then finally, another property is that if one random variable dominates another random variable, then the expectation of that random variable will dominate the expectation of the other random variable, again, assuming the expectations even exist. Because they might not exist, but if they happen to exist as real numbers, then this is what you have. What does this mean? Well, it just means this is a function and that is a function, and we're just saying that this function always dominates. So no matter the random outcome, no matter what sample point you pick in the sample space, the value of this function will always exceed the value of that function. Because this is exactly how integration works. The larger the function, the larger the value of the integral. So these are just some very, very simple properties of expectation. Now we get to something called variance of a random variable. A random variable, and this is another number, another real number associated with a random variable. It's also an important number, just like expectation. So x, this is a random variable. Expectation of x, this is what we've talked about. This is a real number. It tells you what the random variable does on average. And the other number you have is something called variance. This will actually be a positive real number. And when I say positive, I allow the possibility that it could be 0, but it would be equal to 0 only in the most trivial of circumstances. That's not very interesting. So in usual, it's positive. So let's just say what the intuition here is supposed to represent. So a random variable, this is sort of a random real number, right? You do a random experiment, and then you associate to it a real number, and as you keep on doing a random experiment, you keep on producing a list of real numbers, and they're all random. That's why we call it a random variable. You can think of it as a random number generator. Random number generator. A expectation is what the random number generator, right, does on average. So as you generate all of those random numbers, what do they do on average? Like, what do you expect? If you had to take a best guess, what do you expect? And the variance, it measures the spread of all those random numbers. How much are they spread out? So to draw some pictures, here's the real line. And on the real line, you have a bunch of random numbers. And then you realize that most of them appear somewhere in the middle most of the time. There's not that many ones on the outside. And if you were to average them out, maybe this is where the average is. That's what happens usually, right, on average. And the variance just measures how spread out the random numbers are. So for example, let's say the expectation is equal to the number 5. Okay, let's say that's the expectation. So this would be a low variance. And I'll give you an example of high variance. So low variance is maybe you have the number 4.8. You got a little bit below that. You got 5.2, 5.3, 4.7, 5.2, like this. You can see the numbers are randomly generated. Sometimes they're a little bit above 5. Sometimes they're a little bit below 5. On average, they're 5. And there's not too much fluctuation. There's a little bit of fluctuation here. If you have high variance, then maybe you'll have something like this. Maybe you'll have 15, -3, 22, 3, and so on. So the numbers seem to be completely spread out all across the place. They're positive, negative, they're all over the place. And it just so happens that even though they're spread out everywhere, nonetheless, the average of the numbers that if you were to take them will still give you 5. So they have the same average, they just have very different spread. Now, obviously, the lower the variance, the more control you're going to have on the random variable. In fact, if the random variable is constant, its variance will be 0, right? So that would be one case, that would be the trivial case in which the variance would be 0. So it's, in some sense, it's a measurement of your uncertainty. The expectation is what you estimate the uncertainty to be, and the variance is a measurement of how confident you are in making the predictions that you make. So if the variance is very low, you can be a lot more confident that your estimate of the average will be much closer to happening than when the variance is very high. So that's why this is an important number associated with a random variable. Now the question is, how does one define variance? So here's the way we do this. So this is the definition. Let x be a random variable. Now I want you to notice something here, which is very common in probability theory. In probability theory, you often say x is a random variable. You never specify the sample space. The sample space is always there in the background. You always understand that it's hidden out there. So if you want to be more formal, you would say, let omega script a, comma p be a probability space, and x is a function from omega to the real line is a random variable. But we often never write this. We just say, let x be a random variable. It is understood that somewhere in the background, hidden, there is a sample space. But often in probability theory, we never go back to the sample space because, as we've said, the sample space can sometimes be difficult to work with directly. When we have random variables, we're mapping them to the real line, and then we work on the real line because it's a lot more convenient to work on the real line. Indeed, previously when we talked about how you calculate the expectation of a random variable, the way you do that is by using the probability density function. When you look at the distribution of the random variable, that will give you a probability measure on the real line, so you bring everything back to the real line, and then you look at the Radon-Nikodym derivative, and then you use that function to do the calculations for you. That's typically what we always do. We never go back to the original sample space. So this is often the way it's going to be presented. So we have a random variable, and let a be the expectation of x, so a for average. And this is, of course, assuming this exists. It does not have to exist. If it does not exist, if the expectation does not exist, then the variance will not exist either, because the variance depends on the expectation. And then we define the variance of x. This is often the way you write it. Maybe you can also write it like this with square brackets, does not really matter. But the variance of x is equal to, by definition. So I'll write down what the definition is, and I'll explain to you what we're doing here. So you do x minus a. That's the first thing you do. X minus a. So from the random variable, you subtract a. Now, this might seem a little bit bizarre because this is, after all, a random variable. This is a number, okay? So we have to understand that this is a random variable, and this is a real number. So how can you possibly combine them together? Well, all it means is that when the random experiment is done and x is produced, the random number is produced. From whatever number that is, you just subtract away a. That's what that means. You're just subtracting a constant away from a function. That's the meaning of that. Okay, so you just subtract them, and then you're not, because the idea is you're trying to find the spread. So this is the average, and this is one possible value of x. X can be really anywhere on the interval, but this is one possible value of x. And you want to measure this distance between the two. So you do x minus a. You want to measure the distance, and you want to find the distance on average. What happens to the distance on average? So how do you find the average? So this is one possible value of x. Maybe these are like different values of x. So you have different distances that you're getting, different distances, like this, different distances. And you want to just average out what's the average distance that you get away from the average. Now, the problem is if you just take the expectation of that quantity directly, the average of the distances, then that would be the expectation of x minus the expectation of a. This goes back to that property that we mentioned, that the expectation of the sum is the sum of the expectations, and the expectation of x, as we've said, this is what we're denoting by a for average, and the expectation of a constant is just a constant itself, and then you end up with 0. So you will always end up with 0, because really what's happening is roughly half the time, the random variable will be on the right side of a, and roughly half the time is going to be on the left side of a, and the positives and negatives will cancel, and you're left with 0. So that's why this is not the way to do it. And after all, when you calculate distances, you need the distances to be positive. So therefore, it would seem that the way you want to do this is you should do x minus a, take the absolute value of that, because that's the distance, and then you take the expectation of the whole thing. And that you can kind of do it like that, but that actually is called something else. That's called the mean absolute deviation of x. And this is the way you can define it. It's the expectation of x minus a. But variance is defined a little bit differently. Variance is, instead of using absolute value, you use squares. You square everything and you use squares instead. And the question that everyone always asks, and this is the reasonable question, why do we use squares instead of absolute values? So the answer is that for mathematical purposes, squares behave much better than absolute values. It's easier to do math with squares. And that's why we measure the spread using squares and not absolute value. So you could define it, but this one is not actually used much in probability theory. So the theorems of probability theory are all based on this square approach as opposed to the absolute value approach. I'm going to show you later on one of the properties that variance has that's nicer that this one does not have. But you can even go back to something like calculus. If you're integrating something involving squares, that's a lot easier to integrate it than using absolute value. If you have to integrate something using absolute value, as you know, you have to consider where the function is positive and negative, and that's actually not so easy to do. That could be a much more difficult calculation because it's like a piecewise function. You have to break it up into pieces where it's positive and negative and then investigate what happens on each of the pieces. Now, what's also interesting is that there's I think he's an economist, Nassim Taleb, if I'm writing his name correctly, argues that mean absolute deviation is better for applications of probability theory. That what do we mean by better? Better here means that you could make more accurate decisions in the real world. So if you want to make some kind of prediction, maybe involving stock prices or something along those lines, then if your calculations are based on MAD instead of variance, then more often than not, you will be producing better results than someone who relied on variance. So he argues that mean absolute deviation is a more accurate way of working out problems in the real world. It's just that, I mean, he understands the reason why we do it with squares, because for mathematical theory, using the square approach for measuring spread just works nicer in the end. But for making decisions, this would be the way to do it. He actually recently written a book. It's called The Statistical Consequences of Fat Tails. So it's an interesting theme in the book. I do not want to discuss that because that will take us way off topic. He has a conversation with Stephen Wolfram. So Stephen Wolfram has a YouTube channel. You can go there. He has like a 4-hour conversation with Stephen Wolfram talking about the book and what the book is about. So maybe if you're interested, you can look into that. But anyway, this is the way we define variance. And one thing you will notice is the moment you define variance using squares, if the units, so let's say the random variable is telling you some quantity in the units of inches, right? So it produces for you a random number, and the units on x happens to be in terms of inches. Well, then the variance, because everything is being squared, will be in terms of inches squared. So you are changing the units. So to bring the units back, so the units matches what the original random variable is, you would then have to remove the square. And you do that by then taking square roots. And then you define sigma of x. And sigma of x, this is famously what is known as the standard deviation. the standard deviation of x, that would then be equal to, by definition, to make the units the same, you would then take the square root of the variance of x. And you can see the variance of x is a non-negative, it's a positive number. It could be 0 if x happens to be a constant random variable, then this is just equal to 0. But in general, it's a positive number, and you're taking the square root of a positive number. So this is a positive number, and that's called the standard deviation of x. So these are the numbers that we use for measuring the spread of a random variable. So let me just give you a very simple example, and then we finish. So here's an example. Suppose x follows the distribution of a uniform random variable, and it's uniform on the interval from 0 to 1. The first question is, what does this even mean? I know we mentioned this before, but let's just carefully explain what this means. A random variable is producing for you random numbers. And we're saying it's producing for you random numbers on the interval from 0 to 1, and they happen to be uniformly distributed. Now, whenever we talk about random variable, we talk about the distribution. So we're saying that the distribution is uniform on the interval from 0 to 1. What does that mean? It means that if you were to look at the Radon-Nikodym derivative with respect to the Lebesgue measure, it would just be constant. It would just be 1. So it will be the following function on the interval from 0 to 1 and 0 otherwise. So the probability density function, it would just be 0, it would just be 0, and then between 0, it would be 1 over here. So that is what it means to be uniform on that interval. So you will notice exactly what I said earlier. The sample space is not required, because when we say that x is uniform, what we really mean to say is when you look at the distribution of x on the real line, this is the way it looks like. It will produce for you random numbers on that interval, and those random numbers will be evenly distributed throughout the entire interval. So more carefully, what that means is that the function that describes what's happening, the probability density function, it's just completely flat. It has no preference of where you are in that interval, and that's why it goes like this. So let's give this function a name. Let's just call this function f. This is our function f. And now if you want to find the expectation of x, the expectation of that random variable, then the way you would do it is, as we've said, you bring it back to the real line, and you integrate the identity function x against f of x. This is the probability density function. And so this would be the integral from 0 to 1, because after all, this function is 0 outside those bounds, so you only have to integrate from 0 to 1, and it's x, and this function is equal to 1 throughout that interval. So you're just integrating the function x on that interval, and if you integrate that, you get 1/2. Does that make sense? Does it make sense that we get a half? Yes, it does make sense that we get a half, because think about what you're saying. You're saying that your random number generator produces for you numbers between 0 and 1 in a completely uniform way. So if this is your interval over here, and the numbers are just evenly distributed on that line, and there's no preference, it's sort of like the dartboard. It has no preference of whether it is closer to the middle or closer to the end. It's just evenly distributed. Then it would make sense that the midpoint should be the average, right? The number in the middle should be the average, and that's what you have over here. And then you want to find the variance. How would you find the spread over here, the variance of x? Well, how do you find the variance? Well, that by definition would then be, you would have to find the expectation. You would have to do x minus a half squared, like this. So you do x minus the average, right? That's how the definition goes. It's x minus the average. Now, this is going back to what we were saying earlier, that this is sort of like g composed x, or if you prefer, g applied to x. You are applying a function to a random variable. The function here is the function, let's write it like this. The function takes a real number lowercase x, and it gives you x minus a half squared. That's what you're doing. So the way you would then find the expectation is you would integrate from -infinity to infinity, but instead of using the identity function, you use this new function, g of x. So this would just be g of x multiplied against this probability density function, f of x, and then this is the integral from 0 to 1. The reason for this is because this function f of x, it's this function that's equal to 1 throughout that interval. So this is just equal to 1, and then this g of x is replaced by this. So that would be x minus 1/2 squared times 1. And then you can work this out. So this is the integral from 0 to 1. x squared minus x plus 1/4. And if we work this out, this would be 1/3 minus 1/2 plus 1/4. So what is that? So the common denominator is 12. And then we have 4 minus 3 plus 3. Let me just check this again. I made a mistake, so this is multiplied by 4. This is multiplied by 6. Multiplied by 3. 7 minus 6, so 1 out of 12. So that would be the variance. So the measurement of the spread of this random variable would be 1 out of 12. And then the standard deviation would be the square root of that number, which would be 1 over, so 12, 4 times 3. So that would be 2 square root of 3. So that would be the measure of its spread when the units are properly written back in the original units. So that would be the standard deviation. So this is the variance, and that's the standard deviation. So that's the way that you do it. And this concludes our lecture on random variables and their expectations and variances. And you'll have some questions on the homework based on this material.